Yeah, I'm excited to talk to you today about a new project that I've started only in the past few months. We're very much at the infancy of this project, and so we're excited to share it, but excited to kind of bounce ideas off of people and be happy to talk throughout the conference about this. But essentially, we want to build a data-driven model to measure V sin I's of very slowly rotating stars, use this as a jumping off point to measure obliquities of small planets. One of the most common ways to measure the obliquity of a planet is with the Rossiter-McLaughlin effect, where you measure the RV anomaly of a planet during transit, and from the kind of ratio of blue to red light being blocked by the planet, you measure a sky projected obliquity. And this is really great. However, it takes a lot of telescope time to do. It's very expensive. It's a difficult measurement. And so it's also very slow, which is why we've only had about 200 systems or planets with measured obliquities from Rossiter-McLaughlin. The other problem is this method is highly dependent on the radius of the planet. So for very large planets, you could have RV anomaly on the order of tens of meters per second or so. But for very small planets, or even really for the largest of the sub-Neptunes, the RV anomaly drops to 1 meter per second or below, and this becomes almost undoable even with today's extreme precision radial velocity instruments. So we're very, very limited in the populations of planets we can probe from the Rossiter-McLaughlin method. However, there's another way to measure planet obliquity. You can compare the stellar inclination to the transiting planet's orbital inclination. However, in order to do this, you need a rotation period, that's a typo, and you need the V sin I value for the star. Then from there, you can back out the inclination of the star, compare that to the inclination of the planet. And using this method, Lubin et al. In 2024 showed that for stars above the Kraft break, the stars are spinning, the hosts and non-hosts are spinning kind of at a wide range of rates of V sin I values, where the hosts and non-hosts have no kind of relationship to one another, with V sin I being a proxy now for obliquity, given that higher V sin I rates are more likely to be closer to edge on, which would then put the planet obliquity also to be edge on. But however, below the Kraft break at like 6,300 and below, the planet hosts are now preferentially spinning slightly faster than the non-hosts, and again, this is tentative evidence for more generally aligned planets. However, they did end this study at about 6,000 Kelvin, which is pretty hot when we're talking about sun-like stars. And the question is, why did they stop there? And the answer, quite simply, is they kind of had to. Below 6,000 Kelvin, stars are generally spinning slower. This is a plot from the Kraft paper in 1967. Below 1.5 solar masses, stars spin much, much slower. And at slow rotation rates, as we're going to get into, it's difficult to make a V sin I measurement, or an accurate and precise V sin I measurement. And this has big implications because for large planet surveys, we generally like to talk about sun-like stars. This is a couple histograms from the CKS sample. You can see the vast majority of the stars are 6,000 Kelvin and below, and they're also below 5 kilometers per second V sin I. Again, the vast majority of them. So, but in this region of parameter space, it's difficult to measure V sin I from the width of the lines because of macroturbulence. Macroturbulence being like the wholesale movement of like large groups of granules towards or away from us due to convection in the star. And this tends to broaden the lines in a slightly different way than how rotational velocity broadens the lines, but nonetheless it appears in the lines as this like total broadening. And so at very low V sin I values, the macroturbulence becomes kind of equally dominant as the rotational broadening, and this makes measuring that V sin I value very difficult to disentangle from the total rotational broadening. So we have a scenario now where for relatively slow rotating stars, which are most of the sun-like stars, we essentially can't measure accurate and precise V sin I values. And this is the reason why that study stopped at 6,000 Kelvin. But we're still interested in small planet obliquities, and therefore we need these V sin I values. And so that's what this project is. We're trying to build a now data-driven model to measure small, slowly rotating star rotational velocities. So before me, Ida and Isabel introduced the cannon. We're using that a bit as well. But essentially, we're training a model on the CCFs of the spectra itself. Now, the CCF being like an average line profile contains a lot of information about the broadening of the lines themselves. And so we're hoping that now with these really new stabilized spectrographs where the instrument profile is very uniform, we can kind of marginalize over like a hidden parameter of macroturbulence to just measure out the V sin I value. So I spent some time building, oops, that's a little too far, we want to go back. I guess we can't go back.
Wrong button?
Wrong button. So I spent some time, where did that slide go? All right, a slide got deleted. Anyway, spent some time building some hopefully accurate simulated spectra from KPF, where I can tune the exact stellar parameters exactly. I can inject a known V sin I broadening, and from there, plug it into the cannon and try to recover these V sin I values. And so this seems to be working really well. I spun up 1,000 spectra, train on 800, validate on 200. You get this really nice one-to-one line. It's important to note that the simulated spectra that I'm creating have a macroturbulent physical model underneath them. So this is kind of still knowing the answers in the back of the book when I probably shouldn't. However, it's still very promising that we can extract V sin I information from this data-driven model. And this is really pushing down into new regions of parameter space for accurate and precise V sin Is. We're particularly interested in this region below 3 kilometers per second, where other models tend to break down. Essentially, they'll kind of give you an upper limit as to what your V sin I might be if you feed it in a spectrum. But so this is great, but again, this is simulated data. There could be problems with this. This could be too hand-wavy. So we want to do this with real data, but how do you know the V sin I of a slowly rotating star to use as a label into this model if that's exactly what you're trying to discern out of the model? So we kind of got a chicken and egg problem. But what we're going to use is the V sin I that comes from an independent measurement from Roster-McLaughlin measurements. So it kind of all comes back together. So this is a star that's very near and dear to my heart. I worked on a paper this a couple years ago where we measured the V sin I from spec match. It gave us a 2 kilometers per second upper limit. That was great, but we went after it with the Roster-McLaughlin measurement. We got a really good aligned orbit, which is nice. However, we also kind of for free in the model get a V sin I measurement, which is not only consistent with the previous one, but also the error bars now are smaller, and we can work with this now. So I've got an observing program with KPF. We're going after about 50 targets that have had RM measurements previously published. Therefore, they have these spectrum-independent V sin I values. So we know the V sin I is very low. We know it's precise. These are going to be the training labels for this data-driven model. I'll just kind of show we've got one spectrum in hand, for example, showing off how great the KPF data set is, or the KPF instrument is. Really high resolution, really high SNR spectra. And the CCFs are a data product that comes out of the reduction pipeline for free. So I'll kind of stop there. I know I'm the last talk before lunch. Throw out my conclusions, but again, we're really early in this project. And we're trying out a lot of things. I want to experiment more with the cannon. I want to experiment with the pane. I want to experiment with Bayesian neural networks. There's a lot to investigate here. But we think this is really promising in that if we could build a tool where you plug in a high SNR spectrum and you get out an accurate and precise V sin I value, then we can go off and get hundreds of spectra of planet hosts and non-hosts for small planet hosting stars, and start to discern, like, is there an obliquity trend for small planets like there might be for the hot Jupiters. But also, if you have ideas of what you would do with such a tool, I would love to hear about that. thinking about alternative science applications. Yeah, I'll stop there.
Awesome. There's a question right in the front here.
Hi, very cool talk. I was wondering if you take limb darkening into account in any way in your data-driven model.
Right now, it's not a parameter. I could see that being very important when it comes to the RM measurements themselves. I mean, we have models of what the RM measurement should look like, and those do depend on limb darkening parameters, which could affect the measured V sin I, which would then be a label in our model. But no, we're not actually including limb darkening in the data-driven model itself. Yeah.
Hi. Two questions, if I can. One of them is there are known discrepancies between the RM V sin I and the line broadening V sin I. So what do you do in that case? And then the other one is what role do you think resolution has in this? Because if you have a higher resolution, you can resolve the differences from the convection, which is your macro turbulence. So that might help you out there.
Yeah, so as far as the labeling for the training set, we're only going to use V sin I's that come from Roster-McLaughlin measurements. We're not going to use any that come from measuring the broadening of the lines themselves. So we're trying to disentangle the V sin I measurement from the spectra and bring it just to be grounded in the V sin I from the RM measurement. Yeah.
I guess my concern is how well can we actually trust that the RM V sin I one is the correct one?
Oh, I see. I think we tend to trust, or we'd like to trust it more because it's model independent, and because you're getting it from the RV anomaly as opposed to, which is, I guess it will depend on the convective blue shift does come into the RM measurement, but maybe we'll talk later more about that. Yeah.
Great. I think we should probably wrap up here and thank Jack and all of the speakers again.